Okay, give me 30 more seconds.
Okay, no problem.
Ooh, hypothetically, okay. I had a great strategy, but it's my strategy is, oh, there we go. This way I can potentially see who's speaking if they ask questions. So I'm ready.
Okay, very good. So it's my pleasure to introduce Roland Roeder from IUPUI, and he will give part 3 of his mini course on renormalization group and critical phenomena in hierarchical models of statistical physics.
Great, thank you, Jungkook, and thank you to everybody for the invitation to speak here. This is a joint mini course with Pavel Bleher, and he's given the first 2 talks, and I'll give a talk today and on Friday. And here's the abstract from our talks. And we're making the transition from the Dyson hierarchical models to the Migdal-Kadanoff renormalization and hierarchical lattices. And my goal today is to really explain a lot of the physical background of what we want to do with hierarchical lattices. And then at the very end, to explain how Migdal-Kadanoff renormalization works. Then on Friday, we'll start to use dynamical systems techniques to do the renormalization and study all of those things that I described today. So that's the plan. Thanks to Pavel Bleher, Misha Lubitsch, and Robert Schrock for explaining to me everything that I know about the subject. And I apologize for the things I don't know, so maybe you guys can help me when I get stuck. So here's the plan. I want to tell you about the phenomenology of magnets and critical exponents, just to give you a very simple view of what we want to study. And then I will talk about the Ising model. This is the model of magnets, the mathematical model of magnets, one of them. It has a partition function, which is a polynomial. It's a polynomial in 2 variables. It has various types of zeros. It has Fisher zeros in one kind of vertical slice. It has Liang zeros in a horizontal slice, in fact, in any horizontal slice. And it also has an algebraic curve of zeros, if you think about it as a polynomial in both variables, called Liang Fisher zeros. So I'm going to explain all of that in this talk. And in particular, we want to talk about how these behave in the thermodynamic limit. And this is how when the size of your lattice that you're describing your magnet with goes to infinity, the number of zeros or the degree of your algebraic curve is going to infinity, and we want to understand what happens in this limit. That's how you're going to get phase transitions. So then I want to explain what's kind of expected for the ZD lattice. You can imagine the Z3 lattice, the cubical lattice, as your model of a magnet, or maybe the Z2 lattice. And one of the things that's kind of surprising, at least when you first learn the subject, is that very little is known for the Z2 and even less for the Z3 lattice. There are amazing, beautiful things that are known, but there's also a tremendous level of material that still needs to be learned and rigorously justified. So I'm going to explain that. And then there's this really beautiful approximation to the ZD lattice called the Migdal approximation that's supposed to be pretty accurate at low temperatures. But if you do this approximation, it allows you to come up with a renormalization group approach where everything becomes exact after making that approximation. So there's this approximate to the ZD Ising model, and for that approximate, things are exact. And that approximate becomes this hierarchical lattice. So that's what I plan to explain. And I want to go pretty slowly and try to explain everything at a gentle level. I'm hoping that this is useful for students and postdocs. And so I apologize to experts that I'm not going to be saying too many things that are exciting for experts. So that's the plan for today. On Friday, I plan to talk about the Fisher zeros for the DHL. This is several people, but including Bleher and Lubitsch. And then I'll talk about the, this is how my slides go, the names disappear, I'm sorry. This is these next 2 things, the Liang zeros for the DHL, that's Bleher, Lubitsch, and myself. Liang Fisher zeros is the same group of people. And then if there's time, and only if there's time, I want to talk about results on the Cayley tree, which is a different kind of hierarchical lattice. It's like an infinite dimensional lattice in some sense. And that's also a situation where you can use holomorphic dynamics and lots of techniques from dynamical systems to study the Liang and Fisher, and well, there's no Fisher zeros actually, but the Liang and Liang Fisher zeros for this Cayley tree. So if I get time, I will talk about that part too. So so that's the plan. And I want to show you the phenomenology of magnets. And these are the pictures you see in every introductory course on physics, these kind of graphs. And so here, capital T is the temperature, and there is some kind of critical temperature, T sub C. If the temperature is low, below T sub C, and if you look at how magnetic your piece of iron is, you have some sort of chunk of iron, and you want to see how magnetic it is, that's some sense of how well aligned the spins are, you can measure this. And if you, sorry, and if you measure this, and if you vary the external magnetic field H, you'll see that the magnetization, how magnetic your material is, undergoes this kind of jump. For H negative, the spins are aligned with the negative external magnetic field. As H comes down to 0, the magnetization decreases a little bit, And then suddenly when H equals 0, there's this big jump. And suddenly the magnetization becomes positive when H just goes positive, and then it increases and becomes positive like that. So this is some sort of a tremendous discontinuity in the observed physical quantity, the magnetization, as you vary the external magnetic field from negative to positive. So this is what you see. And this is actually why things like the magnets that stick to your refrigerator, like the ones advertising pizza or whatever, why they actually work. Because you can expose your piece of iron, you can imagine this kind of neutral, you expose your piece of iron to, let me use a different color. You expose your piece of iron to some external magnetic field, it becomes positive, and then you come back and it stays positive, and there's this positive amount that it's magnetic even after you turn the external magnetic field off. And this is this phenomenon that makes these magnets that you put on your fridge or that your kids play with. And it's a phenomenon that you want to describe. And in particular, you want to know how big this spontaneous magnetization M plus of 0 T is at a given temperature. This is one of those quantities you want to measure. The non-analytic behavior of M as you vary H when H equals 0, that's what's called a phase transition. And that's what we want to understand is these phase transitions. So that's the goal. And please ask questions at any moment. I'm expecting questions. That's what I'm hoping for. Suppose you increase the temperature right up to some critical temperature. Suddenly your external magnetic field no longer has a jump. Instead, it's continuous, still has the same kind of odd function behavior. It has an infinite derivative. The derivative blows up at 0, but it's continuous. And this is a very particular thing. There's no jump, but it's still a phase transition because the observable quantity, the magnetization, is not analytic at H equals 0. And what's really funny is it's not like a square root singularity, at least for the magnets that we see in real life. For example, for the square lattice Ising model, this singularity here, this is like H to the 1/15th, which is a very strange exponent. And this is one of those things that physicists wanted to explain. You couldn't explain it, I guess, with the sort of simplest mean field theory. You needed a more sophisticated technique to figure out why 1/15th. And for the three-dimensional Ising model, it's another exponent. It's like 1 over 4 something, etc.
Is it always integer?
What's that?
Is it always integer?
No.
No.
So for the three-dimensional lattice, it's 4 point something, but not an integer. And for the diamond hierarchical lattice, it's also not integer, but that's a very strange lattice. Pavel, do you remember it for the Z3 lattice?
Not. I have to look.
You have to look. Okay.
Yeah, I have to look.
It's 4 point something. It's in our paper, but it's not an integer. And it's these funny exponents that people observed in the laboratory that they wanted to explain. And this is part of where the renormalization group technique came from, is to explain this.
But here, is it true 15 or is it 15.000 something?
It's a good question.
No, it's 15.
Okay.
It's 15.
Yeah, it's exactly 15.
Exactly 15.
The two-dimensional case, yeah.
Nice. Okay, so so this is one of those things we want to explain. We want to be able to justify how you get this exponent. Okay. Suddenly you go above this T critical, and your magnetization is just analytic as a function of H for all h. Not even at h equals 0 is there a problem. Everything is fine. Now, on one hand, that's bad if you're trying to make a magnet that sticks to the refrigerator, because you'd expose it to a magnetic field, and then it would just come back down, and you wouldn't have anything when you turn the magnetic field off. But on the other hand, it's kind of good because there's no non-analytic behavior. So already this is the kind of phenomenon that you should hope to be able to describe with your model of magnets. This thing where below critical temperature, you have a jump. At critical temperature, you have some funny exponent, but no jump. And above a critical temperature, you have analytic behavior. This is one of the goals, is to describe that. So there's another quantity that you can study, and that's the specific heat. It's a little bit harder to think about, but the specific heat, this is how much heat you need to put into your material in order to raise the temperature by a given amount. It's some measurement of how much heat you need to change the temperature. And again, there's this non-analyticity. These are all just cartoon graphs, but there's this non-analyticity when you hit T critical. You just go up, you have some sort of a cusp or some kind of a singularity, and you go back down. And the question is how to justify this singularity right at T critical, and how to get the appropriate exponent. And this is not the exponent for the Z2 Ising model. That's a special case, and I guess it's logarithmic for that, not a power. But I wanted to put an exponent so I could say critical exponent. So I think this is for the diamond hierarchical lattice, what I put here. So this is again one of those critical exponents, and the reason I wanted to include this one is this is one that you can study when you have a zero external magnetic field. All of this is at h equals 0, and so it's kind of a simpler case, and therefore it's better understood, h equals 0. And so this is kind of one of the first ones that you can more easily study mathematically. Any questions or comments at the moment?
So is the size of the jump related to the 15? So when in the first picture?
This jump?
Yeah.
It's not. And in fact, the jump will get bigger as the temperature gets lower. And I'm going to explain to you how to determine the size of the jump from the limiting measure of the Yang zeros.
Okay, thank you.
You're welcome. Okay, so let me continue. So I want to describe the Ising model, this model for magnets. And it's going to be kind of a very gentle description. You should imagine you have a sequence of graphs, gamma n. It might be like the n by n square grid, square piece of graph paper, n by n, or it might be the n by n cube, something like this, or it might be something else. And it has vertex set Vn and edge set En, and its size is going to infinity. You're trying to describe something with more and more electrons or atoms at the vertices. And as it's getting bigger, in the limit as n goes to infinity, you'll start to have this critical behavior. So you can think of it as describing the finer and finer approximations to your material. And I like to think electrons, but maybe it's supposed to be atoms, I'm not sure. At the vertices, just think spin +1 or -1 at the vertices. And the spins only interact along the edges. So there's an energetic interaction between spins along the edges. So that's what we have. And the spins are just a configuration of pluses and minuses at each vertex. Here's the energy. So I want to define these first. The interaction is if two spins have the same, if two endpoints of an edge have the same spin, then you get a plus added to your interaction. And if the two spins have opposite signs, you get a minus. And you sum up all of this, and the interaction is big if the spins are very well aligned, and it's small, meaning negative, if the spins or small, if the spins are very misaligned. And so we want something that will favor the spins being very well aligned. Meanwhile, you can also just take the magnetic moment of sigma. This is just the sum of all the spins. This is the conglomerate, how much spin you have. And the point is that your energy of a configuration is minus J. J is a coupling constant times the interaction. So that means that if the spins are very well aligned, your energies, that term is very negative. It makes a very low energy, which is easier to achieve. And then minus h times the magnetic moment. So if your spins are very well aligned with h is just a scalar, external magnetic field. If your spins are pointing very much in the same direction as h, then that'll bring your energy down. If they're in the opposite direction, it'll bring it up. And so this is the energy, okay? So there's a problem though, is that you have 2 to the cardinality of your vertex set number of states. And so even for the 10 by 10 square lattice, which is ridiculously small from the sense of statistical physics, you're going to have 2 to the 100 states, which is some big number. I put it into maple to look impressive, but it's just some tremendously big number. And so that's really hard to work with. And so you have to go to probabilities. And the assumption, the Gibbs-Boltzmann hypothesis, is that a state sigma occurs with probability proportional to this Gibbs weight, Wn. Everything's indexed by n. You have this gamma n plus 1, these bigger and bigger lattices. And the probability of sigma is proportional to Wn, which is e to the minus energy of sigma divided by temperature. It's the first place where temperature comes into the story. And so the idea is if the temperature is very, very low, the states with the very low energies will be singled out. They'll be much more probable than the states with the higher energies. So you'll really be focused very much around the lowest energy states. But then as the temperature gets higher and higher, the higher energy states start to come into play and they're more equally probable. Finally, as t goes to infinity, all of the states are equally probable. So it's this kind of balance between trying to favor energy versus this randomness coming from increased temperature. So this is the sort of standard distribution that you use. This is the same distribution as Ableher was using in his talk. This is a simpler version of it, but it's the same thing. It occurs in basically every statistical mechanics talk. And you have to normalize, you have to divide by the sum of all of the weights. So the probability of state sigma is its weight divided by the sum of all of the weights. The weights probably don't sum up to 1. And this guy here, this Zn, it's a function of h and t. H is the external field, t is the temperature. And it's called the partition function. And somehow the theory is set up in a way that this function basically governs everything. Your normalizing constant, studying that tells you just about everything that you want to know. And so that's really great. And so we're always going to be talking about the partition function, and this normalizing factor, the sum of the weights. And you should worry. You should worry about those places where you would divide by 0. At those places where you would divide by 0, your model is going to have a big problem, right? So that's kind of a problem. Does it happen? This is the question for postdocs and students.
You need high school students to.
Yeah, I'm sorry. It's too easy for you guys. You guys are too advanced. So of course it doesn't happen. The Gibbs weights are positive, right? So you're summing up positive things. So of course it's not ever happening. But that's only true if h and t are real. And therefore, when h and t are allowed to be complex, if you complexify them, you could have zeros of this thing. And it's those complex zeros that are going to give you phase transitions in the limit as n goes to infinity. Those complex zeros they can come in and accumulate onto the real slice. And this accumulation of complex zeros to the real values of h and t, that's where you get phase transitions from. So it's a really strange thing. For finite n, this partition function is just fine. But the complex zeros can come and accumulate, and that's what I'm going to show you in several descriptions. So these h and t's, this is some sort of transcendental function, these Gibbs weights and the partition function, and it'd be good to use a polynomial instead. And so there are various choices of variables, but these are the ones we'll use. This little t is a temperature-like variable, So t is between 0 and 1 is the physical range. I'm sorry, whenever I advance my slides, the writing disappears. Z is minus h over t. This is a magnetic field-like variable. And this would be like z is between 0 and infinity for h and t. Well, h real, t greater than 0. So these are the physical values of these. But using these makes the system, I have it in my slides. Using these makes the partition function much simpler. The Gibbs weights are just monomials in square root of t and z. It's just a matter of normalization having this square root. And the partition function becomes a polynomial in square root of t and z, except that it can have some negative powers. So it's some kind of Laurent polynomial in z and t. And so you can write it out like this. Its degree in z is the cardinality of the vertex set divided by 2. And it's a symmetric, actually, in z goes to 1 over z. The reason is that if you switch all of the spins, if you just flip each of them from whatever spin they had to the opposite, the interaction stays exactly the same. Bonds that had the same spins at the endpoints still do. Bonds with opposite spins at the endpoints still have opposite spins. But the magnetic moment flips. And so when you do that, such a term as the Gibbs weight, the t stays the same, and the z flips to 1 over z. And so you get this symmetry in z goes to 1 over z. So ai of t is the same as a minus I of t. This is a symmetry of the partition function. And yeah.
Can I ask a question? So
Sure,
what is the role of this capital J? So you call it a coupling constant?
That's just a coupling constant. And basically, you could assume that it's 1 because it gets absorbed into the quotient j over t. Yeah.
Okay.
Yeah. Some people consider the Ising model on with a j negative, where the coupling prefers you to have opposite spins, but that's a different story. So for us, the j is positive. So this is this fundamental symmetry of the Ising model. And at some point later in, probably on Friday, it's going to play a role. So I wanted to point it out. But the key thing to observe here is that up to some square roots, and this being a Laurent polynomial, this is just a polynomial in z and t. So it's a kind of a nice function. It's not a nasty function. So when you have the partition function, physicists also define the free energy, which is again a function of your field-like variable z and your temperature-like variable t. It's defined to be minus t times log of the absolute value of your partition function. One reason people do this is that this will be useful when we want to take the limit as n goes to infinity. This is a more natural thing to work with when we try to take the limit as n goes to infinity, but it shows up in physics independently. And so you can actually compute the magnetization at finite n. It's the expected value of the magnetic moment of sigma over the Gibbs distribution. It's this nice, nice derivative of the free energy. And so it's immediately related to the free energy in this nice way. Similarly, you can check that the specific heat is expressed in terms of a second derivative of the free energy. And so the moral of this is that, first of all, since the partition function is non-zero for all the physical values of z and t, these thermodynamic quantities, the magnetization and specific heat, they're analytic functions of z and t for finite n.
Why function of zt you differentiate by h?
Which one?
Why function fn of zt, of variable zt, you differentiate via h?
Because I want to use the chain rule, and that's the formula that I need, unfortunately.
And in second formula, vice versa, you differentiate by t, capital T.
Right, right. So you got to use you've got to use the chain rule.
Okay.
Yeah, I believe it actually is correct, but it is strange. Pavel and Robert, is it right?
No, this is right. Yeah.
Okay.
Yeah, that's fine. Yeah.
Okay, I'm greatly relieved. Okay, so it's funny when you do these calculations, when you really do them by hand, you see these funny aspects of it, but that's just how
No,
it works.
maybe the only thing that when you define free energy, you have to divide by the number of degrees of freedom.
Right, yeah, I'm going to do that in a little bit, actually.
Okay.
Yeah. So, so these are funny formulae, and it's absolutely beautiful, in my opinion, that the magnetization works out this way. It's an easy calculation. I don't want to do it, but this is something you can do in, following the definitions, you can do it in 10 minutes after the talk. It's just a direct calculation. So that's the first remark, is that these thermodynamic quantities vary analytically in Z and T over the physical values of Z and T, Z being positive and T being between 0 and 1, because the partition function is non-zero there. So if no phase transitions for finite n. And the other remark is that basically, if you want to study phase transitions in any of these quantities, magnetization, specific heat, there are others that are derived from free energy, it's sufficient just to consider singularities of the free energy. That's enough. That's the kind of granddaddy of all of these thermodynamic quantities, and you can just study it. That's the kind of principle. So that's what we're going to do. So this is just kind of a remark. This is a funny notation, but you can clear denominators. And if you clear denominators, I make this a Z check, you get an actual polynomial in Z and T. So occasionally I'm going to use that instead of Z. It's just to have an honest polynomial. And then the free energy, this is a kind of nicer version of the free energy, and people from physics probably will be horrified. But if I just take log of the absolute value or modulus of this polynomial, I'm going to call this a kind of nicer version of the free energy. It's just to make things conceptually easier. Studying this is equivalent to studying the actual free energy. But the point is, it's really cool because this is the pluripotential, or distinct potential if you like, for the zeros of the partition function. So this potential theory that people from complex analysis and complex dynamics like, it gets beautifully tied in with the notion of free energy. So this is perfect. So in certain situations, instead of studying the classical free energy, we'll study this variant just to avoid kind of ugly denominators and weird terms. It doesn't matter for the actual kind of core idea of what's going on. Okay. Everybody happy and ready to go forward? It's supposed to be a course, so I have to teach. Okay. So to get phase transitions, we have to take n to infinity. And I'm actually going to describe 3 different situations where we take n to infinity. I want to talk about it in 3 different levels of difficulty in some sense. And so to get phase transitions, we're going to take n to infinity. And I want to start with the simplest case. All of this can be discussed when h is 0, which is the same as having z equals 1. So this is 0 external magnetic field. It's much simpler. It's still very complicated and interesting. And so let's talk about that for the next 10 minutes or so. And in that case, the partition function becomes a univariate polynomial. Again, I'm working with the one whose denominators have been cleared. And so it's a univariate polynomial, and the zeros, these are zeros in the complex plane, and the complex T plane are called Fisher zeros, named after Michael Fisher. And these zeros, then it turns out that the free energy, this redefined version of the free energy that I wrote, is exactly the logarithmic potential for these Fisher zeros. So that works out very nicely. If I did the classical free energy, there'd be some extra capital T and there'd be some extra log of something that wouldn't matter for phase transitions. So if you took the weak Laplacian of this free energy, you get exactly the suitable sum of Dirac masses, Dirac measures at each of these Fisher zeros. So you can think either about the free energy or about the sum of Dirac measures at these zeros. That's the kind of equivalence. And so the first thermodynamic limit you could think to take is just set h equal to 0, try to take the thermodynamic limit in the complex T plane. And I'm going to call this is not a standard terminology, but I'm going to call this the complex temperature thermodynamic limit. And so as Pavel mentioned, you really need to normalize by the degree of your polynomial when you try to take a limit. And so we're going to divide by the cardinality of the edge set, the number of edges. That's the degree that the partition function has in T. And we're going to say that the lattice gamma n has complex temperature thermodynamic limit if these normalized finite n free energies converge to some limiting function in L1 loc of C. So this is a kind of funny definition, but I want to make some point about it. So you could alternatively look at the, not quite a probability measure because of the 2 pi here, but you could look at these measures nu n located at the Dirac masses, Dirac measures at the Fisher zeros, and you could ask about whether these measures have a limit as n goes to infinity, and that's equivalent to the lattice having a complex temperature thermodynamic limit. And so, and you can actually write that the limiting free energy, if this complex temperature thermodynamic limit exists, the limiting free energy is exactly the logarithmic potential over this limiting measure. So you can either think about limits of the free energies or limits of the measures, and they're equivalent. And so just to point out that comparison. In certain situations when we're doing dynamics, we often, it's easier for us to talk about the measures, but it's equivalent to the free energies. So I want to tell you a couple of situations where it was proved that the complex temperature thermodynamic limit exists. And so Onsager proved it for the Z2 lattice. This is his famous Onsager solution. I didn't write it in our variables, I didn't convert it, but this is the formula for the limiting free energy on the Z2 lattice at 0 external magnetic field. So I put a picture of Onsager because it's fun to see pictures of people. And so this is the free energy. And so it justifies the complex temperature thermodynamic limit for the Z2 lattice. And it also tells you that the limiting distribution of Fisher zeros is, if you study this equation, is supported on the union of these 2 circles. And so these are the circles. I think it's a t minus 1 equals square root of 2, and t plus 1 equals square root of 2 are the circles. And so this is a kind of cool thing, because in particular, as you're varying your temperature from 0 to 1, the fact that there are just these 2 circles tells you exactly that there's a single point where the free energy can be non-analytic. And Onsager's solution, you can study it, you can see exactly how it fails to be analytic at this TC. So you can compute basically everything about this phase transition at TC from Onsager's solution.
And the limiting measure, will it be singular or?
So it'll be supported on the union of these 2 circles.
But,
I believe it will be absolutely continuous relative to the arc length measure on those circles.
okay, so
I don't actually know the details of this as much as the Liang part. But let me mention one kind of funny thing is that for finite n, the zeros might not lie on these circles. For finite n, you could have some zeros that aren't right on the circles. But as n goes to infinity, the limit of the measures, the limit of the Fisher zeros converge to these circles. Okay. So that's one thing. To show you that there are other situations where it's known, our friend in the audience, Robert Schrock with Matveev, they showed some really cool behavior for the heteropolygonal lattices. So if you look at these so-called bathroom tile lattice, then there's actually also a similar solution to the Onsager solution. There's an explicit formula for the free energy, and you can study it. And what's really crazy is you get these whole regions like this, where the, well, like the inside of that, where the free energy is not analytic. Is that right, Robert? Did I?
So it depends. we looked at the various Archimedean lattices, and there's some where the support still lies on a one-dimensional manifold. For example, for the triangular lattice, the hexagonal lattice,
Mhm.
and several of the heteropolygonal lattices, they're again one-dimensional algebraic curves. What we call the 488 lattice, this bathroom tile lattice, is special in that regard. Anyway, yeah, it's an interesting case. Yeah.
Yeah, I wanted to show that something really wild can happen, and
Yeah, right.
it's a nice picture. So, so again, I mean, you could study the phase transitions as you go across here, or if you're really good with potential theory, and you can analyze the phase transitions, the singularities of the free energy anywhere in this complex plane. So that's really interesting. But what's also really interesting is that, and this came as a surprise to me, it seems that when D is bigger than or equal to 3, the classical ZD lattice, including Z3, this complex temperature thermodynamic limit isn't known whether it exists. And I find that quite surprising. I mean, the Z3 Ising model should somehow be the model of magnets. And even this kind of simplest complex version of the thermodynamic limit looks like it's not known. And people can correct me if I'm wrong. I'd be happy to be wrong here.
So, of course, exists depends on whether you're a physicist or a mathematician. Okay, you're probably right as far as rigorous mathematics is concerned. The physicists, as you know, are more sloppy, so they're kind of happy to proceed. But for D greater than or equal to 3, it's you know, I agree with you. There are a lot of deep questions concerning the nature of these singular manifolds, word varieties. Yeah.
Is there a formula that they believe, kind of like the Onsager formula for the Z3?
No. That's, in fact, people searched for that for decades. It was a
Right.
fruitless search, and
it's not supposed to be an exactly solved thing, right?
Exactly,
Yeah.
and then it kind of, you know, the emphasis shifted from the, you know, this kind of closed form analytic result to a focus on universal behavior, and in particular
Right.
critical exponents. So
Right.
that was, as you know, that was a big aspect of the renormalization group, that
Right.
for the universal behavior, it didn't matter if you had a non-Sager formula.
Right.
You could still describe the universal behavior. That's what's so nice about the renormalization group.
Right. Right. So it's a curious thing. I mean, you learn about the Ising model and you feel like everybody has proved everything, but it's actually, there's much less known than you would expect. So I want to make the transition.
Can I ask another question regarding the previous slide?
Yeah, sure.
So,
sorry.
I mean, this lattices, you approximated by some finite sublattice, and then you ascend n to infinity. And does the limit depend on this approximation, which one you choose? Or is it clear that it does not?
So I'm going to let Robert.
So in physics, we define various what we call boundary conditions. And there are two simple ones you can consider, so-called free boundary conditions or periodic, or they're also so-called twisted boundary conditions. And the existence of the thermodynamic limit is predicated on exactly the condition that it should not depend on the boundary conditions, okay? Now, people define, for example, if you use free boundary conditions with a magnetic field, there's a kind of trivial dependence, namely what your external field is on the boundary, because that'll bias the system to you know, below the critical temperature to have a magnetization up or down. But that's a trivial kind of dependence. Aside from that, it should not depend on the boundary conditions.
Excuse me, let me give some comment. You see, in my opinion, it also depends, first of all, on the infinite graph. Is it amenable or not amenable? Because in amenable case, there is a limit that physics call one-hole limit.
Right.
And in the group theory, we call Fellner's limit by Fellner subsets.
Right.
This is one thing. Another thing is that you can exhaust your infinite graph by finite subdomain, considering the different boundary conditions, but you also can approximate by finite quotient. It's like in group theory, approximate infinite group by finite quotients. And in 1985, I published paper note with my advisor at that time, Stepin Anatoly, on the approximation of ellipse measures on infinite graphs, infinite groups by this finite group. So there are various approaches to this method. And by the way, there is a very interesting article by Lunda, Regge, and Rossetti, where they study Ising model on modular group, on Kelly graph of modular group, and where they make computation using phoneme and trace. And I think the approach is wrong, but there's another method. Okay, thank you.
Thank you
Well,
very
one
much.
comment there, of course, is that physically, what we mean by this independence of boundary conditions is essentially that the volume should dominate over the surface. Okay, the trouble with the Cayley graph is everything is the surface. So
Right.
you know that's a kind of very special case.
Right.
Is every graph amenable in physics? Or do
Oh, beta lattice is not amenable.
Exactly. That's just the Cayley or the beta lattice does not have the property that the so-called internal volume dominates over the surface, because, as I said, everything is the surface.
and that graph is relevant for physics? Okay.
I mean, I guess it depends on who you ask if
Well,
it's relevant for physics, but
Yeah. Okay.
I
Well, maybe I
personally
should
like it.
apologize. Yeah.
Okay, so let me continue with this. This is great. So now I want to switch to, instead of having H equals 0 and varying T, I'm going to fix the temperature and I'm going to vary the external magnetic field. And so this is the perpendicular direction. And before, remember the picture with the specific heat. The picture with the specific heat, that was the thing you study with these Fisher zeros. Now I'm going to try to describe those curves for magnetization where you have a jump, or you have a critical exponent, or you have an analytic behavior. And so this is about the Li-Yang zeros. And there's a really amazing theorem in the geometry of polynomials that if you fix your temperature-like variable between 0 and 1, these are the physical values of your temperature-like variable. And then if you study the zeros in the field-like variable z, lay the eye on the unit circle, mod z equals 1. And so this is a amazing theorem. I have some pictures here. This is really beautiful because it doesn't depend upon your graph even. So as long as you have this ferromagnetic coupling, J being positive, for any graph, it could be the complete graph, it could be the Cayley tree if you like it or don't like it, it could be the square lattice graph. It works for any of them. And so it's a really amazing theorem. And you see this theorem, basically in algebra, it tells you if you're looking in the complex Z plane, the only place where you could have a phase transition is right there at Z equals 1, because that's the only place where the complex zeros of the partition function could accumulate. And so it's an algebraic theorem that tells you that the only place where you could have the phase transition when you're varying H is when H equals 0, which corresponds to Z equals 1. So it's really amazing to prove a theorem in algebra that has such a consequence for phase transitions. And so this is a wonderful theorem. It's funny, people are still thinking about the algebraic aspect of the Li-Yang theorem. So Ruel published a paper about the Li-Yang theorem kind of recently, and so did Borsia and Brandon. They published several papers about it kind of recently. So it's really a kind of big business, this Li-Yang theorem. And it's very, very exciting. One of the things that it does, beyond just telling you where the singularities for your free energy could potentially be in the limit, it allows you to do the thermodynamic limit in much greater generality than in the Fisher zeros. So I want to talk about the thermodynamic limit. And so a more classical definition of thermodynamic limit, if you asked a physicist, would be something like this. And I think this should be the cardinality of the vertex set. I'm sorry about that. The normalized free energy, as n goes to infinity, converges pointwise on the physical values z is positive, t is between 0 and 1 to some limiting function. This is a more kind of standard notion of thermodynamic limit. And as Grigorchuk mentioned, this is a consequence for many lattices, the amenable ones, of Van Hoff's theorem. So there's a famous, wonderful theorem that tells you that this exists for these classical lattices. What's nice about this is that assuming this, then it follows from the Li-Yang theorem, because you know that the singularities of the free energy have to be on the unit circle, and Montel's theorem, that if you have this classical thermodynamic limit, then there's a limiting measure of Li-Yang zeros. And in fact, the thermodynamic limit exists in the whole complex Z plane in that sense. So it's much more general, the situations where you can study the limiting measure of Li-Yang zeros than where you can study the limiting measure of Fisher zeros, which is kind of surprising because Li-Yang zeros should be harder to study. When you have such a limiting measure of Li-Yang zeros, you can write the free energy as, this time I'm not getting rid of the funny terms, so I just made them in yellow here so you can not see them. The free energy is basically, again, the logarithmic potential over the limiting measure of Li-Yang zeros. The magnetization is the Cauchy transform of that measure, up to, I think there's a 2 pi that people usually put. And this here, this is the jump. This is the size of, well, it's 1/2 the size of your jump. This is the spontaneous magnetization. This is equal to the, if your limiting measure of Li-Yang zeros is absolutely continuous with respect to Lebesgue, this is the density of that measure at angle 0. So if you look on the circle, and if you look at the, remember this was the physical Z, if you take the density rho right there, that density of the limiting measure of Li-Yang zeros is exactly how much spontaneous magnetization you have. So it's a beautiful description. And so again, the point is that if you understand the limiting measure of Li-Yang zeros, and in this case, it depends upon a parameter t between 0 and 1, your temperature. If you understand it for all t, then you understand the phase transitions when t is fixed and z is varied. Okay. And for example, there's this jump that I showed you at the very beginning of the slides, this jump where you go like this jump. That's exactly related to this limiting, the density of the limiting measure at angle 0. So this is a funny slide. And so there's a kind of conjectural description of what the limiting measure of Li-Yang zeros should be for the Z2 lattice. And so I want to describe it to you. So this is supposed to be the Li-Yang cylinder. So temperature is vertical, is between 0 and 1. This is T equals 1. And I'm just going to show you what height you're at in the top. And here, when T is 0, it's easy to check that the Li-Yang zeros are the nth roots of -1. So they're distributed according to Lebesgue measure. And when T is small, it's expected and indeed proved that the Li-Yang zeros have this limit with positive, it's absolutely continuous with respect to Lebesgue measure and has a positive density. And there's still the magnetization, the density at 0. My slides stopped updating somehow. Okay, now you can see it, okay. So you still have this jump here. Suddenly you get to T equals Tc, critical temperature. And the Li-Yang zeros should still be absolutely continuous, but they should have a vanishing density at angle 0 that vanishes like phi to the 1/15th. This is for the Z2 lattice. This 1/15th is the same 1/15th as we saw for the picture of the magnetization, for the critical exponent of the magnetization. And it's predicted by this Wilson-Fisher renormalization theory. It's not rigorously determined. And then you get to T above Tc, and suddenly there should be a gap around 0 where you have no Li-Yang zeros, and the measure should still be absolutely continuous and supported off of that gap. And people people have proved that there is an angle where you have no zeros. And finally, you go to T equals 1. This is infinite temperature, and all the Lie zeros are at the end. So this is the picture. And what I want to try to convince you, I've actually done this, by the way, I'm sorry about this, but I've done this for Z equals e to the minus 2h over t instead of Z equals e to the minus h over t, which is what we were doing. This is a different normalization, but it doesn't really matter. So I want to show you a really cool numerical simulation of the Lie zeros done by Arturo Garcia Saez and Suche Wei, who's from Stony Brook. And they studied they approximated the Ising model by an approximation called the tensor networks. And then they made these plots of the magnetization, and the jump in M of Z as you cross the circle should be your density of the measure. And so here at TC, they don't have a plot in their paper below TC, but at TC, you see you have a jump everywhere on the circle, and then maybe there's something not clear there. But above TC, you have this nice slope where you have analytic behavior. And so somehow this is a numerical confirmation of the picture that I described for you here, this work of theirs. And I find that quite exciting. Of course, it's numerical, and it's a numerical study of a model of the Ising model. So that's tricky, but it's interesting. So what I'd like to do, we had this critical exponent, this 1/15th, and I would like to explain how that's related to the 1/15th for the singularity of the Lie zeros. So here's a proposition that will be useful for relating the limiting measure of Lie zeros to the critical exponents as you pass through them. So here is a logarithmic potential of a measure. I'm going to do a probability measure on the real line. And the theorem is, if you look at this quantity, this limit, or the proposition, you look at this limit of the measure of the short interval. So you've got, here's R, you look at 0, and then you take the short interval minus delta, delta. You take the measure of that short interval relative to the Lebesgue measure, but you do it with logarithms, then you can take this limit. This is called the pointwise dimension of I guess I called it, yeah, of mu. And so it's a very common definition. And the statement is that then, if you look at the logarithmic potential for that measure, and if you study it just along the imaginary axis, f mu of I, y, then there is a analytic function so that if you subtract it, your f mu of I, y has a singularity with critical exponent exactly kappa. So the critical exponent is equal to the pointwise dimension. So this is a very nice thing, because it's kind of, in dynamical systems, it's often pretty easy to compute these pointwise dimensions, and this allows you to relate them to the critical exponents of the free energy. Does that statement make sense? Okay. So there's actually a discussion of this kind of implicit in the end of the paper from Misha and Pavel back in 1991 about the pointwise dimension versus the critical exponents. So this can be helpful, and I just want to show you how it would work. You see, remember that here was our density rho of theta. Here's theta at critical temperature, T equals Tc. The conjectural picture was that the density was like this, right? Rho of theta was like theta to the 1/15th, right? This was the picture from the conjectural description of Lie-Yang zeros. And then this is telling you that if you go through, if you pass through here, here's theta equals 0, that then the free energy, this is S or something, then the free energy is going to have this singularity with the same exponent. So maybe I should, sorry, this isn't set up so well. F of S minus 1 is like S minus 1 to the 1. Well, so this actually 1/15th is not the pointwise dimension because you need to integrate. And so the pointwise dimension here would be kappa is equal to 1/15th plus 1 because that's the density. So 1 plus 1/15th. Let me clean that up, I'm sorry. F of S minus 1 should be like S minus 1 to the 1 plus 1/15th. If you trace through what this proposition means, and if you believe this conjectural picture for the Lie-Yang zero measure at the critical temperature, and then the point is that the m is what, minus d dh of f, and so m of S minus 1 would be like S minus 1 to the 1/15th, which is exactly the critical exponent that we saw in our original pictures. So I just want to show you that this proposition is really useful, and it connects the kind of how sporadic the measure is on the circle with how singular your free energy is as you cross transversely through it. That's what I'm trying to demonstrate. Okay, so I think I've got 5 minutes. So I want to talk about the Lie-Yang Fisher zeros, and then I'm not sure if I'll get to the Migdal approximation and Migdal-Kadanoff renormalization yet, but I wanted to explain all the background. So you can consider the zeros of the partition function not just at fixed z equals 1, or not just at fixed t. You can consider them as a single algebraic curve in C2. Let's call it Sn. And as n goes to infinity, the degree of the curves goes to infinity. They get more and more complicated. And the question is, what happens? Can you take some sort of suitable limit of these zeros? And if you want to do that, you want to use the notion of currents. And by definition, a 1,1 current on C2 is a continuous linear functional in the space of 1,1 smooth forms that have compact support. So this is the kind of analog of measures or analog of distributions, but instead of eating test functions, they eat test forms. And so the kind of one of the favorite examples is the current of integration over an algebraic curve C. And what does it do? You denote it by C with the square brackets around it. It eats a test form. It eats a test form eta by just integrating eta over the smooth part of C. This gives you, associated to each test form, it gives you a complex number. So this is your basic example of the current. And so we're going to do that for the Lie-Yang Fisher zeros Sn. We're going to look at their currents of integration. This will be analogous to the measure supported on the Fisher zeros or the measure supported on the Lie-Yang zeros. This is kind of measure theoretic version of this algebraic curve. And the natural question is, if you normalize by the degree of the curves, do the currents normalized by the degree of the curves have a limit as n goes to infinity? This is for some lattice. So you've got some lattice. gamma n, and associated to each n is the partition function. It has the zero locus, which is this algebraic curve Sn. If you consider that algebraic curve as a current and normalize, can you take a limit as n goes to infinity? It would somehow extrapolate between the Fisher zeros on the vertical complex T slice and the Li-Yang zeros on the real cylinder. And so that's the question. And so this would describe the limiting distribution of these so-called Li-Yang Fisher zeros. And if you were restricted to almost any complex line, this would describe the limiting distribution of slices by that complex line. So it's some sort of, as Misha likes to say, it organizes the zeros into some object, this current. And so if you think about the free energies, which are these log mod of the partition function where I've cleared denominators, these free energies are exactly the pluripotentials for these currents. These currents are described as the distributional derivative DDC of the free energies. And so if you wanted to prove that the sequence of currents up here converges to a limiting current S, that's equivalent to proving that the normalized free energies in C2 converge in L1 loc to some limiting free energy. So this is again, a kind of statement of there being a thermodynamic limit, but now in all of C2. So it's a different kind of thermodynamic limit. And that's equivalent to saying that these currents given by the nth level Li-Yang Fisher zeros, suitably normalized, have a limit. And so in that case, we would say that gamma n has a global thermodynamic limit, so in all of C2. Unfortunately, it seems to be unknown for all of the ZD lattices when d is bigger than or equal to 2. So very little is known about it. On Friday, I'm going to talk about it for the diamond hierarchical lattice. So it's true for DHL, which I'll be defining, I think, on the beginning of the talk on Friday. So what I was hoping to do today was just to give you a picture of what all of these objects are. And then on Friday, then I'll explain how in this approximation to the Z2 or to the ZD lattice, we can actually study these objects quite effectively using Migdal-Kadanoff renormalization. So I should probably stop there. So thank you for listening, and
Thank you, Roland.
thank you, Misha.
Questions or comments?
So could you remind maybe so how this critical exponent can be expressed in terms of the renorm transformation? So in terms
Right.
of the eigenvalues, etc. This 1/15th. So what is it?
Right. So
where it comes from dynamically?
let me explain it slightly differently. Let me explain for the Fisher zeros. So if you look at the Fisher zeros, here's the complex plane, and then there's this TC here. Here's 0. Here's 1, and then you have this kind of. I'll show this on Friday. I don't have it prepared in my slides, but you have this kind of Julia set coming in. And the free energy, F of T is this, up to some adjustment, is this integral over C, the logarithmic potential, T minus zeta d mu zeta. And mu is the measure of maximal entropy of the renormalization map.
Mm-hmm.
So you mean for this one or for the Wilson-Fisher?
Whatever. So it seems that whenever you have renorm transformation, you
Right.
have such a
Right.
formula. So, but even
So let me do it for this one, since I don't actually know how to do it for the Wilson-Fisher. So this is the Migdal-Kadanoff renormalization. And what happens, there are two ways to look at it. Way one is that basically the singularity for the free energy f of t minus tc should be like t minus tc to the kappa, where kappa is the pointwise dimension of this mu. But then the pointwise dimension of mu, you can compute it. Basically how you taught me when I was a postdoc is you can compute it by taking small disks, and then you iterate r to the n times until they're of some definite size. Now I'm overemphasizing how big it should go, but you iterate n times until it gets big. And then, so mu of r to the n of, call it the little one, d, is on the order of 1, right? So that implies right. And then n is, the point is that if you look at the lambda is the multiplier, r prime of tc, so lambda to the n equals if you call this a d sub epsilon, lambda to the n times epsilon is on the order of 1 because you're trying to get to the disk of radius 1. And so the point is that log n log lambda plus log epsilon is like 0. So n log lambda is like minus log epsilon. But maybe instead of doing the formula, I just say it with words. You determine from your multiplier at the fixed point how many iterates it takes for the epsilon disk to get definite size and therefore achieve definite measure. On the other hand, you know how much measure there is in the epsilon disk. Mu of d epsilon is like 1 over the degree of your map to the n mu of d1. And so it's this interplay between the degree, and your measure transforms by the degree, but the size of your disk transforms by the multiplier. And you use this interplay, and then you get kappa. Kappa is equal to log the degree, which is 4, over log lambda if you do estimates kind of like this, which maybe I won't try to do them in front of everybody.
And I guess this is quite general formula, so it's just,
right.
So this 1/15 also comes from this kind of considerations for the Z2 model.
So that's a question that maybe Pavel or Robert can answer. I don't know actually.
So, and if it does, why it is 1 over the integer? So I'm coming back to Dima's question.
Arithmetic
so again,
dynamics.
in general, it's not an integer, right?
But why in that model it has?
The RG doesn't require integer critical exponents. But what Roland said is correct. From the point of view of Migdal-Kadanoff, block spin renormalization, real space RG, you linearize the RG transformation in the vicinity of the critical point, and you read off the exponents from that linearization, which I guess Roland will talk about on Friday maybe, but that's the basic idea in real space RG of how you get these exponents.
Yeah, well, it is. Yeah. So what will place the role of degree in that model, in the standard Z2 model?
So let's see, what do you mean by degree again?
So here we have the ratio of the characteristic exponent of the fixed point to the log of the degree, or the other way around. The degree is equal to 4 of this norm transformation. So
yeah, I'm sorry, you mean the vertex degree on your lattice? You don't mean that?
Probably it is, yeah.
Oh, no. The RG is independent of the vertex degree. If, for example, for a triangular lattice, the vertex degree is 6, right? But in the ferromagnetic Ising model, or any ferromagnetic model, according to usual RG arguments, the critical exponents would be the same. Namely, they're independent of the details of the lattice structure, at least for the ferromagnetic case.
Let me ask the question in the following way. So if you apply Renorm transformation and look how this limiting measure mu, so Lie-Young measure, is transformed under this transformation. So what will be the transformation rule? So in this model, the measure is multiplied by 4 by the degree of the map 4. It is a measure of maximal entropy. And in that model, it will be multiplied by what?
So Misha, you're defining your term degree is different than a graph theory term, I think, right? You're defining it more in terms of these.
In this case, it is just the dynamical degree of this rational map, which is the
Okay, fine.
normalization.
Right, so that's going to differ in general from the vertex degree as defined in graph theory.
May I say a word? Maybe wasn't the question why we have something like integers? Doesn't that come from the fact that, for example, in the 2D Ising model, the critical exponent is just some power of 2, they're always like rational numbers that can be easily guessed. And, if you take the logarithm of 4 divided by a logarithm of another power of 2 that one can determine, then you get a rational number.
So what would you say, Robert? Would you agree with this interpretation?
I mean, again, the critical exponents in general are not rational.
Right.
The two-dimensional case is special, and the way we view that is in terms of conformal algebra, that the scaling dimensions of operators, in other words, here you add a critical exponent, you have scale invariance because the correlation link goes to infinity. But in fact, in 2 dimensions, you have not just scale invariance, but conformal invariance. So the work of Belavin, Polyakov, Migdal, Zolnojikov, others shows that these scaling exponents can be derived from the Virasoro algebra. So I would say that's what would underlie the rational values for 2 dimensions. But again, when you go to 3 dimensions, it's not true. I mean, there has been a lot of work done on that recently using bootstrap conformal field theory methods. So there's a lot of intensive research on that at present. But you don't expect rational values in let's say 3 dimensions.
Yeah, but wouldn't 2-dimension wouldn't one call this case trivial if it's like, just some algebraic quantity like you mentioned? 3-dimension, it's kind of like the Gaussian fixed point where you can compute all the eigenvalues. There are cases like the 2-dimensional Ising model where you can compute what these exponents are.
Oh, sure, but that's not Gaussian. That's the
No, I know, but
yeah.
not Gaussian, but you can compute it via some algebraic thing exactly. And then it tends to be some nice number, like a power of 2.
Right. And the way you understand that, it's true, of course, that when, for example, when Yang computed the beta equals 1/8 for the magnetization, or any of these other critical exponents, you can understand that from exact results. But the nice thing about the conformal field theory was that it's very general. Namely, you could add so-called irrelevant operators to your Hamiltonian. It wouldn't make any difference. The Onsager result would not go through in the same way, in the sense that you can't get an exact analytic result for the free energy or the magnetization, but the universal critical behavior as embodied in the critical exponents is the same.
So there is underlying some conformal symmetry which is responsible for this rationality. That's what you're saying?
Right. That's right, yeah. That's our modern view of it. But
So
again, the
that-
people who actually discovered these things like Fisher and, you know, and Yang and so forth, Kadanoff and so forth, that kind of predated the more recent work on conformal field theory by BPZ and others.
Okay, thank you.
So let me just comment that I don't personally know how to relate the Fisher zeros to do a renormalization at the level of Fisher zeros coming from the block spin classical renormalization. That would be kind of a dream to be able to do that, I think. So I'm not completely sure to what extent this type of picture that was drawing for the Migdal-Kadanoff renormalization can be generalized, but it would be nice to understand it better.
Just to make sure, so your calculation on the last page, do they essentially say that the critical exponent is the growth of the linearizer map? So if I remember,
on this page here.
yeah.
So the critical exponent is the growth of the linearizing map.
If I remember correctly, the growth of the linearizer map is log degree over log multiplier.
Yeah, that's the formula. Yeah.
So that it makes sense. So what you're doing is kind of linearizing the picture and then say that the critical exponent is the.
Yeah. I think that makes perfect sense. Yeah.
That is sort of this Young formula for the dimensions.
Yeah, exactly. It's like this Ladrapia-Young formula.
Yeah.
So for people who didn't like my crazy whiteboard explanation, this was going to be in the very beginning of my Friday talk. So I'll do it better on Friday. So
on Friday, you will focus on Migdal-Kadanoff already. Okay?
That's my plan. I was going to explain where it comes from by this Migdal approximation to the Z2 lattice or the ZD lattice, just to kind of motivate it. And then I was going to show that basically all of these problems can be studied pretty effectively with that. Does that sound good?
Sure, yeah.
Okay.
And could you remind? So most of the talk, it was the complex plane, and only at the end it was C2. So could you remind how did you fix the variable in the beginning?
Right. So the well, I'll just write. So first of all, we had T is temperature.
Yeah. So you have two natural variables.
H is magnetic field. Yeah.
Yeah.
And then we did little t was e to the minus j over t, where j was the coupling constant.
Yeah.
Which you could just suppose j equals 1 if you like. And then little z was e to the minus, and I think I had a 2 on the little t. Little z was e to the minus external magnetic field over t.
Yeah.
And so physical values, this was like t is between 0 and 1, and this is like z is in 0 infinity. And the first thing, so if you look in C2, I mean, drawing C2 is always kind of funny, zt, then you can look at z equals 1, you can look at the kind of complex plane over z equals 1. This is the Fisher. Zeros live in there. There's some sort of Fisher zeros, right? And then you can also look at kind of the cylinder. This is t is between 0 and 1, and mod z equals 1, and these are the Li-Yang zeros. And in particular, I mean, you fix a height, and then you look at the zeros on that height. And then finally, you can just look in all of C2 all at once, and you get some kind of algebraic curves. I mean, it's hard to draw algebraic curves, I guess, but there's some sort of algebraic curves Sn in there, and they hit the Fisher slice in some finite number of points, and they hit the Li-Yang well, if they hit the Liang cylinder in some kind of curves that hit different heights at different at finitely many points. And so you can look at the Fisher zeros just in the complex plane. You can look at the Liang zeros either at a given height or on the whole cylinder, in which case they become a lamination. Or you can look in all of C2 at these algebraic curves, and they kind of all fit together.
C2 is more natural setting because the renormalization transformation naturally acts on both variables. It is just because of these horizontal slices.
Right.
So that's why, whether we want this or not, we better leave in C2.
Right. So it's a very lucky thing that it preserves the Fisher slice, so that makes that easier, and it preserves the Liang cylinder, but the Liang cylinder is already two-dimensional, and so it's.
I see. Thanks.
You're welcome.
Other questions, comments? If not, let's thank the speaker again.
Thank you.